I'm Chenxing, a researcher at Shanghai Tree Graph Blockchain Research Institute. Today, I will introduce our work in building an efficient authenticated storage, which is helpful for improving blockchain performance. Blockchain systems offer secure, decentralized, and programmable ledgers for transactions. Nowadays, assets in tens of billions of dollars are managed within these systems. However, early blockchain systems were hindered by low throughput, processing fewer than 30 transactions per second, which is significantly slower than centralized systems like Visa. Fortunately, recent research designed efficient protocols to address major bottlenecks in blockchain system, including transaction broadcasting and consensus protocols. Now, transactions can be disseminated to the blockchain nodes and consensus can be reached efficiently. Now, we encounter a new bottleneck, transaction execution. The execution layer of the blockchain is impacted by the slow storage access. Our research reveals that the storage access can consume up to 80% of the total execution time. Today, I will discuss our efforts in developing an efficient blockchain storage to enhance the overall performance of the system. Now, let's take a closer look at the execution layer of the blockchain. Here, a stack-based virtual machine processes the transactions determined by the consensus protocol, executing them in accordance with the opcodes. When a read operation is encountered, the system first seeks data from the cache. If it's not found, it fetches the value from the storage and pushes it to the stack. Because the keys used for accessing storage are dynamically generated during the execution, it is not easy to predict and prefetch the accessed keys before execution. Consequently, the process of loading values from the database can block the execution and become a bottleneck. For the write operations, the chains are written into the cache, which will be flushed to storage in batch after the execution of one block. Storage access in blockchain is slow because the key value pairs are not directly stored in a database, but are kept within an authenticated data structure, which is then saved in the database. So, a single read and write operation at the application layer can translate into 4 reads and 8 writes as a key value database, according to our experiment. This read and write amplification accounts for low storage speed in blockchains. The authenticated data structure here is a key part of the blockchain system. After executing the transaction in a block, each node is tested with computing a commitment from the post-execution storage in a determined rule. This commitment is subsequently incorporated into the block header. Whenever a client requests the storage values from the server returns both the request values and the proof with respect to the most recent commitment. The client having access to the commitment from the block can validate this proof. This mechanism is designed to safeguard clients against potential deceptions by malicious servers. As the blockchain systems assume clients have the correct block headers, this verification process ensures the accuracy of the results. Cryptographic tools play a pivotal role in enabling this mechanism, notably the vector commitment protocols. Currently, almost all authenticated storage rely on the Merkle tree. The earliest blockchain authenticated storage, known as MPT, and the subsequent improvements are designed based on it. In the Merkle tree, each node is the hash value of its children. So when a value changes, the nodes from the corresponding leaf to the root will be updated accordingly. This takes logarithmic time. However, even if logarithmic time is considered a practical cost in cryptography, it brings read and write amplification in authenticated storage because each node represents a key value pair in the backend storage. A write operation involves reading and writing of nodes along the entire path. Improvements based on MPT can only alleviate this theoretical overhead but cannot eliminate it. This cost hinders the performance of all above systems. Hence, we ventured beyond the Merkle tree to find new vector commitment schemes. We settled on AMT. It removes the necessity of maintaining inner nodes and allows for constant time commitment. This means that we can develop a more efficient solution based on AMT. We have other reasons for choosing AMT, which will be discussed in the following part. Although AMT offers potential advantages, we face several challenges in tailoring it for practical blockchain application. First, there's a matter of complexity versus practical speed. The Merkle tree operates in logarithmic time, but generally proves faster in practice because AMT has a slow elliptic curve multiplications. Second, AMT's scalability poses a problem. It requires public parameter of a size equivalent to its capacity. Therefore, if an AMT can store up to 100 million entries, 100 million public parameters will be kept in memory, a heavy demand on system resources. Lastly, there are nodes that serve clients and generate proofs. However, maintaining data for proof generation requires logarithmic time. In the first challenge, we need to tackle the expensive elliptic curve multiplication operations. In AMT, when an element is updated from AI to AI prime, the commitment undergoes the following update. In this process, elliptic curve multiplication consumes 19.2 microseconds, taking up most of the time. However, if we assume that all updates are +1 operations, then we can sidestep this expensive elliptic curve multiplication. Therefore, our solution was to design a version-based database. Each key comes with a version number that increases by 1 with each update. By using AMT to store version numbers instead of values, we bypass the expensive elliptic curve multiplication operation. For all values changed in the block, we store the key, version, value tuples into a Merkle tree. Given that this Merkle tree remains unmodified afterwards and the amortized complexity is constant, no database is necessary during its creation. To validate a value, we use AMT to prove its version and use Merkle trees to confirm the value under the given key and the version. The second challenge we faced was related to AMT's scalability. As introduced before, AMT takes a number vector as input, generates and maintains a commitment along with other information. However, this process has several limitations. First, the scale of AMT's input needs to be determined at the setup phase and cannot be dynamically expanded. So we need a sufficiently large K as a setup phase. Second, AMT relies on pre-compute parameters equal to the input scale and access them randomly at runtime. So we need to keep parameters in line with the maximum ledger size. Third, the blockchain has a 256-bit key space, which is much larger than a feasible key. So we need to extend AMT with some dynamic structures. In LVMT, we adopt a multi-level AMT structure and dynamically allocate slots in AMT for storing version numbers. First, every input element in each level of the AMT can expand out into a sub-AMT. This multi-level structure makes LVMT infinitely scalable. Secondly, the version number slot for key is determined at runtime. When a key changes for the first time, LVMT will start from the root AMT and look for a vacant slot for this key level by level, according to the key prefix. Once a slot is allocated, it will be permanently bound to this key. Since blockchain nodes execute the ordered transactions with consensus, the allocation of version slots are consistent. The third challenge concerns serving clients. Maintaining a commitment only requires constant time. But if a node needs to serve clients, it must spend logarithmic time maintaining auxiliary information. Since the overall throughput of the blockchain system must ensure that every node can execute transactions on time, the cost of maintaining proof shards also hinders overall performance. Here, AMT also presents a tree-like structure, but we notice that this structure differs from the Merkle tree. In AMT, Maintaining commitment does not require the inner nodes, so the nodes can ignore them unless it serves clients. But the Merkle tree requires all the inner nodes to compute a correct commitment. To lower the maintenance burden, we distributed the responsibility of maintaining the auxiliary information data across multiple servers based on key prefix. All the nodes will maintain the version number and the commitments. Besides that, the proof sharding nodes additionally maintain a subtree in the root AMT and the corresponding sub-AMTs. It will also maintain a few nodes in the top layers. This approach significantly reduces the maintenance cost for each individual server. With this method, community members can participate as a consensus nodes with low hardware requirements, thereby increasing the decentralization of the network. In contrast, specialized client service providers often employ more nodes for load balancing. They will significantly benefit from this proof sharding design. In our evaluation, we developed a modularized evaluation tool. Here, modules are interchangeable and interact via a unified interface. On the backend, our experiment employs RocksDB. In the authenticated storage, we evaluate different versions of LVMT. LVMT-R, designed for consensus nodes, only maintains commitment. LVMT followed by a number refers to the fraction of proof shards. We also compare LVMT to MPT and other improvements. The test workload includes randomized tasks with different ledger size and real Ethereum data. This diagram represents throughput across various workloads. Our LVMT-R significantly outperforms both MPT and RAIN by a minimum of 300% and 80% respectively. While managing a shard of auxiliary information, LVMT64 and LVMT16 achieve approximately 80% and 60% of LVMT-R's throughput respectively, still maintaining an advantage over other schemes. LVMT1 underperforms in all aspects, underlying the significance of proof sharding. We also evaluated the ability of LVMT to resolve read-write amplification. In this figure, we found LVMT-R almost eliminated the read amplification for existing keys, and LVMT can keep better performance when ledger size grows. This is because the two-layer LVMT can accommodate 20 billion version numbers. Here, RAIN blocks has some values less than 1 because of its own caching mechanism. We also launched an end-to-end experiment on a blockchain node Conflux to demonstrate the impact of the overall performance. For simple transaction transferring, LVMT-R is up to 2.7 times faster than MPT and 1.7 times faster than RAIN, underlying the substantial performance improvements brought by LVMT in the blockchain systems. In the time breakdown of the transaction execution, we found that LVMT-R and LVMT64 achieved performance close to direct operations to the database. LVMT also significantly reduced the maintenance cost of the authenticated structure. This demonstrates that LVMT has indeed effectively reduced the overhead of authenticated storage. As a conclusion, LVMT utilizes superior vector commitment protocol AMT, offering higher optimization potential. Through the version-based design, multi-level AMT, and proof sharding, LVMT addresses challenges effectively. As a result, LVMT enhances the execution throughput of the blockchain system by up to 2.7 times. That's all for my presentation. Thanks for your time and attention. See you in the question and answer session.